Okay. So I'd like to thank you for welcoming. I'd like to thank you for coming to another one of QFI seminars. So today we have Professor Kaden Hazzard from Rice University. So Professor Hazzard got his Bachelor of Science in 2004 at Ohio State University. Then he got his Master of Science in 2009 at Cornell, and his PhD also in 2010 from Cornell. From 2010 to 2014, he was a postdoc at JILA at the University of Colorado Boulder. Now, from 2014 to present, he was assistant professor at Rice University. So he's the recipient of a numerous number of awards, including the Springer Thesis Award in 2010, the AI Grant Fellowship in 2017, the New Journal of Physics Outstanding Referee in 2017. He was a fellow of the Institute of Quantum Science Engineering at Texas A&M University, and most recently he got the NSF Career Award in 2019. So please help me in clapping virtually Professor Kaden Hazzard.
Excellent. Thank you, Joshua, for the nice introduction. It's great to be here and to get a chance to share things online with you. It's not the same as if we could sit around and have lunch and coffee, but it's the next best thing, and really excited to chat with you. Feel free to interrupt at any time. I know that you can't just unmute yourself, but please, anytime I say something that's confusing or just unmotivated, or you don't know why the hell I'm saying the things I am, just stop me and we can chat about it. Good. So also, if anybody wants to chat afterwards or something, feel free to send me an email, and I'm happy to have Zoom calls one-on-one to address any curiosities you have. So I'm going to be telling you about stuff that is pretty new. So in fact, everything I'm going to tell you here, almost everything I'm going to tell you here, is totally unpublished. It involves both the theory work that I do. I'm also going to show quite a bit of data from experimental collaborators, and it's going to be on two separate topics. So one of them is on essentially what the frontier of quantum magnetism with SUN systems is in ultracold gases. And the second topic is going to be about this very vague sounding notion of the structure of correlations of many body systems. And what I really mean there is, if you're familiar with the technical term, Lieb-Robinson bounds, so how fast information can move or how fast correlations can move in a quantum system, but also some of the applications that haven't been recognized, and especially how to use it to improve the rigor of numerical methods and improve the methods themselves. So before diving into that stuff, let me make sure this is working. Uh-oh. Okay, there we go. So let me show the my collaborators who have, of course, done all the real work. So the SUN results on the theory side have been almost exclusively, the ones I'm going to show you are almost exclusively by Eduardo and Hao Tian, who are both Rice grads, really excellent Rice grads, and collaborator Richard Scalatar, a professor at UC Davis. On the experimental side on the SUN, all of the work is, I'm going to show you, is by Yoshiro Takahashi at Kyoto. And of course, just like me, he's not the one that did the experiments. Here's a nice picture of the people who did the actual experiments. In the age of Zoom, I guess they paste all these pictures together. So, and then in the second half of the talk, it's really these error bounds and Lieb-Robinson bounds are really the work of a fantastic graduate student, Ji-Yuan Wang, who has done these. So let's give a general overview of what's going on in the group. I just put up this slide to point out that there are lots of things going on in the group that I'm not going to talk about today, from new numerical methods or unconventional superconductors, quantum algorithms, things like that. But if you're interested, feel free to get in touch. So let's jump into the topics I wanted to talk about today. So I want to talk about SUN magnetism, and I guess this probably doesn't need a ton of motivation for this audience, but I want to give some background so you can see where I'm coming from and get used to my accent and all of that. So, so here's a picture. This is a picture of ultracold atoms in an optical lattice. In this case, it's a two-dimensional square lattice, which you can see by the grid of lines that's been drawn on here. And I don't know why I always use this picture, because it's not the most ideal looking picture, but actually experimentalists, I see there's a question here. Okay, maybe a Zoom bomb question there. So there is, Sorry, I've never experienced these Zoom bombs either, so I will
Yeah,
probably be
sorry.
amused the whole time it keeps happening. So anyways, this is a square lattice. There are atoms in this lattice at very cold temperatures of nanokelvin, and the incredible thing is that we can image every single one of these atoms. And this is not like an STM image where you're getting an average density. This is an instantaneous measurement of all the atom positions, so that you know exactly where every atom is, and you can extract correlations by averaging over lots and lots of shots of these. You know really what's going on in the system. And the whole reason this is possible is because at low temperatures, things move slowly. And when things move slowly, you can manipulate them with light, right? So I can send in a photon and the atoms get pushed around by the photons, which they don't very much at room temperature, but at these very low temperatures, it's a different story. So that's really why one of the big reasons we like to work with ultracold matter. And just to continue on this theme a little bit, here's an Eiffel Tower built of ultracold matter. This is actually just an image of the traps that would hold a bunch of atoms. So you can get this kind of single site control and imaging in whatever geometries you want now. It's getting to that point where we can construct very complicated structures, and you can build a Hamiltonian on a structure like this. So if you want to explore an Ising model on the Eiffel Tower, we're getting there. It's very close to being a reality. And to give you a more typical picture of the sort of systems that I'm thinking about in this talk, we're going to be thinking a lot about lattices. So if you put atoms in a periodic structure of some type. And I like this picture mainly because it's pretty, but it also gives you a sense of the sort of scale of what's going on. So, so you have some atoms and a bunch of lasers that hold them in a trap, and then if you zoom in on this, you can see there's this nice lattice structure which is formed by counterpropagating laser beams. These counterpropagating laser beams form some sinusoidal interference pattern, which can give you a periodic potential that the atoms or molecules or whatever you're trapping experience. But to give you this, the nice thing about this picture is it gives you a sense of the scale. That things are 532 nanometers apart, not apparent from the picture, but the sort of spatial scale, how many sites are involved, right? So you can see this is maybe a 10 by 10 by 10 lattice. The actual physical systems are roughly on that order, maybe a little bit bigger, maybe it's closer to 20 by 20 by 20, or even in some cases, something like 100 by 100 by 100. So they're large, very large compared to what I can say put on a computer and simulate, but they're not infinitely large, and they're not a mole of particles large. So a typical atom number is 100,000 atoms for a 3D system like this. And so there are dozens or actually hundreds of experiments going on with systems like this in the ultra-cold atoms community. And the reasons that we're really into this are because of the control of these interacting mini-body systems that you can get. And it's also because the form of this interacting mini-body system is very interesting, right? So a typical form of what you get when you put atoms in a lattice, if you have fermionic atoms at least, what you're going to get is this should say SU2 Hubbard model. That's a typo. That's good. Later we'll see SUN. But if you take spin 1/2 fermionic atoms and put them in a lattice, you get an SU2 Hubbard model, which probably most of you are familiar with. But real quickly, what you have is a nearest neighbor tunneling between adjacent lattice sites at a rate t, and you have an on-site interaction u that if two atoms are on the same lattice site, that's the energy cost. And usually it's repulsive. It's actually tunable for us. We can do attractive or repulsive models. Both are pretty interesting. But we'll be thinking about the repulsive case here. And this is a famous model in solid state physics. Of course, some people think maybe it captures the essence of the cuprates and high temperature superconductivity. It's this very fundamental model, but despite its simplicity to write down, we really don't yet have a controlled understanding of even what its phase diagram is, especially the ground state phase diagram. And there's lots of progress being made, but there are still no conclusive answers. So in the cold atoms community, there have been a lot of experiments on this SU2 Hubbard model, where they have explored the equation of state. So things like how does the density change with chemical potential? What's the compressibility like? They've explored this in 1D, 2D, 3D lattices. They've done it in dimerized lattices, I believe in honeycomb lattices, lots of different lattices. They've seen non-equilibrium dynamics. So you can, for example, start in a fermionic mod insulator, and you pull a particle out. So you have a hole, and you can actually watch how that hole moves around. And because this is a strongly interacting system, it's not at all trivial how that thing moves around, right? There's an interplay of the movement of that hole with like the spin fluctuations and the charge fluctuations of the background. And so people have studied that, and they've seen string correlations, not just 2-point correlations, but how do string correlations grow? But maybe the most direct connection to what people are interested in the solid state community who study these things are that people have begun to observe antiferromagnetic correlations in these gases. So this is the tendency: if I have one site where the spin points up, the adjacent sites point down. And in the case where you get to low enough temperatures, at least if you're in a three-dimensional system, you get some long-range order. So this has been studied in 1D, 2D, 3D, and cold atoms. But actually, every single experiment that has been done so far is in the regime that I'm kind of indicating on the right here. So to reach antiferromagnetism, you have to get on this T squared over U type scale, which I'll discuss in a second, tunneling squared over interaction. And that scale is really a sort of nanokelvin or maybe 10 nanokelvin scale. And the experiments have not gotten that cold yet. So they can see short-range antiferromagnetic correlations, and short-range may even mean out to 5 or 10 sites, but they don't actually get into the antiferromagnetically ordered phase where you'd have a true long-range order. And of course, the really exciting thing would be to get a little bit colder and see if there is actually this superconducting phase that is predicted upon doping. So this is a putative cartoon of a, this is a cartoon of a putative phase diagram. We don't really know what happens when you dope the system. And by doping, I mean move away from one particle per site. But we would like to know. And so we're on the cusp of being able to explore that with ultracold atoms, but we're not quite there yet. Okay, so that's kind of the background of what I want to get into about why we're going to look at SUN and some background for what we're going to see. I guess maybe I should just quickly say then, are we all happy with this background? I'm assuming that a lot of us are solid state physicists and have sat through a million talks on Fermi Hubbard and things like this. But if you have any questions, please just stop me now. Okay. I'm not seeing any hands raised, so I'm going to power forward. So this brings me to the SUN side of things. And maybe surprisingly, this actually means we have to look a little bit more at the actual atomic physics of the situation, right? And I think this is also really cool if you're coming from a solid state background. You may hear these talks where somebody cools a new type of atom or something like this, introduces some new technique, and you're wondering like, why? Haven't they cooled enough atoms by now? Why do we need another one? And this is a good example of how advances in atomic physics techniques and cooling new atoms, things like this, can lead to fundamentally new capabilities for controlling strongly interacting matter. So typically the experiments you hear about are with alkali atoms. That's this first column of the periodic table: lithium, sodium, potassium, rubidium, cesium. But what I want to talk about today are alkaline earth atoms, or alkaline atoms. And those come from the second column of the periodic table, or I guess a terbium counts for some bizarre reason. We'll see what the special properties are that actually we need to have an alkaline earth atom, or alkaline earth-like atom. So we can look at the way that interactions work in alkali atoms to sort of give you how a typical ultracold atom experiments works. And then I'll tell you what happens with the alkaline earth atoms that makes them so special. So here's an alkali atom. It looks a lot like hydrogen because all the alkali atoms look a lot like hydrogen. They have some nuclear spin and they have an electron spin. The hyperfine coupling of an atom means that the nuclear spin and the electron spin are not really independent things, right? So they are just different, they're locked together somehow. So just for a mental picture, they're pointing in the same direction or anti-aligned or something. So the point of what's going on to understand collisions and interactions in a cold gas is that the interactions between two atoms are really almost entirely controlled by the Coulomb interaction between the electrons and the nuclei. Right? So whatever the electrons are doing, that's what's really telling you the effective interaction potential between atoms. And so you're going to get a very different collision depending on what the relative orientation of those electron spins are, right? So if I think about the interaction energy, the Coulomb interaction for two aligned electrons as a function of position, it's going to be very different than if they're anti-aligned. I mean, just because of the wave function changes because of the Pauli exclusion. So the collisions are very different depending on if the spins are aligned between the two atoms or anti-aligned or rotated in some direction. So collisions depend on the electron spin, and because we have this hyperfine coupling, it means collisions depend on the nuclear spin. You can't even really talk about nuclear and electron spin independently. And this is where alkaline Earths are different. So think for a second what's different. Well, they're in the second column of the periodic table. It means they have a filled shell, right? And so since you have this filled electron shell, it means the only spin degree of freedom comes from the nuclear spin. And so there's no difference in what the electrons do, regardless of where this nuclear spin points. So now the collisions and the interactions are totally independent of that nuclear spin. And that's what gives us the higher symmetry. That's what gives us this SUN symmetry instead of an SU2 symmetry. And thanks to another happy accident that occurs, which has to do with nuclear physics rather than atomic physics, the nuclear spin can be huge in these systems. So you can have up to 10 nuclear spin states in this system. So for strontium, you have 10 spin states, or if you want to think about it this way, it's a spin 9/2. For things like ytterbium, you have 6 degenerate spin states. So not only do we have an enlarged symmetry, that n can get pretty big. And in one experiment, you can tune from n equal 2 to 3 to 4 to 5 to 6 all the way up to 10. And you can explore all these different n in an experiment. Okay. So your first reaction might be, okay, that's great, but doesn't this just become classical? Right? So as in, Chris, you have a question?
Just give me 1 second. I believe you're unmuted now.
Yeah, I think I'm there now. Thank you very much. Yeah, I just wanted to ask, so is it the case then that the SUN is in principle approximate in the sense that there'll be higher order processes where I kick an electron into a higher orbital and then it can, yeah.
Very good, Chris. So, so in fact, you also have SUN symmetries in solid state. They're just approximate. You have some different valleys in graphene, or you have some multi-orbital compound, and a lot of people use SUN as an approximation. And so the question is, is there a comparable situation here? And of course, my answer is yes. In life, there's no such thing as an exact symmetry. Who knows what's going on at a Planck length or something? But here, actually, the symmetry holds to extremely high accuracy. So because there's a separation of energy scales between the kind of nanokelvin scale or maybe microkelvin scale interactions that we have, and the kind of atomic structure where you have, well, different units, but 13 eV or EVs of excitation energy, the SUN symmetry is predicted to hold to something like 9 decimal places. So it's approximate, but it's an extremely good approximation. And the experiments haven't verified it to 9 decimal places yet, but they verified it to something like 3 for at least some aspects of the interaction. So to 1 part in 1,000, we're very confident that these are exactly SUN symmetric. Or to 1 part in 1,000, we're convinced that they're SUN symmetric. And so that's really important. This isn't just like a simplified picture or a cartoon. It's really a very, very accurate approximation. Okay. So, and if that doesn't answer your question, please, just follow up. But so the first objection might be large n sounds great, but isn't it just classical? Large spins are supposed to be classical. You have more components, but the fluctuations only grow like the square root of the number of components, so the fluctuations are negligible. And so let me disabuse you of that idea. So first, let's think about an SU2 case, and we can think about why it does become classical. So for something like an SU2 case, at least for a typical Hamiltonian, you're going to have something like S dot S, right? And so now as that S becomes large, S dot S can only raise or lower the angular momentum by 1 unit, right? So I can, maybe on one of these atoms, I can go up 1 unit, and the other one I go down 1. But the fluctuations induced by the Hamiltonian are kind of finite. They're plus or minus 1, whereas my spin gets really big. So the fluctuations are small compared to the absolute size of the spin. In contrast, for SUN, you can have interactions that exchange you between any two states. And I'll show you why in just a second. You're just permuting the two states. And so you can have arbitrarily large quantum spin fluctuations, even when n becomes infinity. And for that reason, for this special symmetry class, the large n limit does not have to become classical. And so let me show you a little bit more about what the model is. So if you put n-component atoms with this SUN symmetry in an optical lattice, now you just get the Hubbard model, same as we did last time, except we have this sum over sigma, which is now not just down and up, but it's red, blue, yellow, green, something. So it's 1 through 10 or 1 through 6, depending on the system you're working with. And the interaction is likewise independent of the sigma and sigma prime, just like we saw when I was discussing the collisions. Okay. So that's not classical. The model looks very similar to what we had before. In fact, the basic mechanism of the physics in a lattice is very similar to the SU2 case. So for SU2, you have this super exchange process which wants to anti-align the spins in the ground state. And the reason you can do it perturbatively, but it's actually not just a perturbative argument. The point is that if two spins are aligned, they can't get past each other. And so it costs a lot of kinetic energy by Pauli exclusion. But if they're anti-aligned, now they can get past each other and it's going to be lower in energy, right? And so spins would rather be anti-aligned than aligned. And in the limit that u is much greater than t and you have 1 particle per site, the energy scale for this is that t squared over u that drives the antiferromagnetism. Okay, so the point is things want to anti-align, and this works for SUN just like it does for SU2. The only difference is what I mean by anti-align for SUN is just that two adjacent sites or two particles want to be in different spin states, but they don't really care which pair you're in as long as it's different. All right, so what do we get out of this? It's not classical, supposedly, is what I said, and we're driven by super exchange. What do things look like? So let's think about the starting place we often start with for these Fermi-Hubbard models. 1 particle per site, u is much greater than t. This is a very interesting regime, so that's why I'm starting here. And let's start about, I'm just going to talk about 2D here, but there's really interesting stuff going on in 1D and 3D as well. So if you have SU2, you get this checkerboard pattern of antiferromagnetism that we're probably used to, this nail state. It's quasi long range ordered at 0 temperature. If you have a 3D system, it becomes true long range order. For SU3, you get maybe an analog of that that's not so surprising. So some pretty reliable numerical calculations give you this stripe pattern, where I have a line of yellow sites, then a line of red sites, then a line of blue sites, and this just repeats. So not so different from the n = 2, just a larger, enlarged unit cell. For SU4, it starts to become more interesting though. So for SU4, the pattern actually becomes something that looks like a valence bond solid. So you form a singlet, by which I mean red-green minus green-red. So that type of singlet on a pair of sites. And you form that and tile the plane with these sort of bonds, these singlets. But the singlets aren't the same everywhere. So you alternate between having a red-green bond and then a blue-yellow bond and then a red-green bond back and forth. So you have this sort of intertwined spatial symmetry breaking due to the formation of the singlets and the tiling of singlets, but also a spin rotational symmetry breaking due to the fact that it's red-green on one pair and then blue-yellow on the next pair. So that's more interesting. And then when you get to SU5, here's a really funny pattern. I'm not sure how reliable the numerics really are here, but it's, you know, they've done some fantastic work. And this is actually a periodically ordered pattern, but maybe with a slightly more subtle type of ordering than the simple stripes. And if you go even larger, you are predicted to have things like spin liquids. So fractionalized states where even though you have spins, which are bosonic degrees of freedom, the emergent excitations are fermions. So this is super exotic. Of course, people get excited about it. Of course, you probably won't be surprised that as you go to larger n, the numerics becomes less reliable. The methods become less reliable. And so And so the predictions become more exotic, and those things may be correlated, right? There's always that aspect of it's more fun to see exotic things than to just see a broken translation symmetry. But we do know in some controlled cases that when you go to large N, if you change the filling just right, that there's actually a controlled theory that lets us see their spin liquid. So there's a really rich phase diagram, and it's a lot of fun, and who knows what we'll find. That's something we're working on. And in addition to N being a control parameter, there's the fact that doping is a control parameter. And by doping, I just mean moving away from one particle per site. And for SU2, maybe this gives us the D-wave superconductivity. We get pseudo gaps and strange metals. We get all this fun stuff. For SU3, 4, 5, higher, to my knowledge, this has not been explored at all. Nobody's even done a simple calculation of what might happen if you dope a SU3 system or SU4 system. And so this is something which we're working hard on at the moment to try to just do some simple approximations and figure out what might happen. Do you get exotic superconductors? Do you get some different state? And I don't really have a good feeling for this yet. So instead, what I want to tell you is the state of the art of where experiments are and what we've been doing theoretically to understand those experiments. And so let me present to you the experimental results. This is a plot of the correlations measured in the experiment. And the precise correlations I'm talking about are given by this formula here, the CNN, up to a proportionality factor. And in words, what this is, it's measuring how likely are spins on adjacent sites likely to be in different colors or different flavors, right? So to not be the same color. But not in it doesn't get large in a trivial way that if I make N large, but with no correlations, so of course you're more probable to be in different configurations, but this correlation doesn't increase for that trivial reason. So this is really a measure of the sort of correlation-driven propensity to be in different spin states. Okay, so here are the results. We're plotting that correlation as a function of the entropy of the gas. And this gas in a lattice. So this system is in a harmonic trap, but if you want to, just forget about that and imagine it's one particle per site everywhere. That's a fair first approximation to this. So the blue data points at the bottom here are what you get for a one-dimensional system with N equal 2. So the usual SU2 gas. And you see that you have to get below about maybe 2 kb times the number of particles, entropy, and then you start to develop correlations for SU2. Excitingly, for SU6, the correlations are much, much bigger. So they're a factor of 3 bigger, maybe it depends what entropy you're at. They're even well over a factor of 3 bigger at the higher entropies, but they're a factor of 3 bigger. And they onset at a much higher entropy. Okay. So this is exciting because not only with SU6 do you have access to new types of physics, maybe you have access to it at higher entropies. And if you remember back to the start, I told you one of the difficulties with the cold atom SU2 experiments has actually been getting to low enough temperatures. The SUN may provide a route forward to this, that the temperatures may be more accessible here, or the entropies. So let's see if we can understand this. The basic thing I want to understand is why are correlations bigger for SU6 than they are for SU2? Okay. So let's think about a very simple limit. Let's think about a Mott regime. So U is much greater than T. You have 1 particle per site. There are no charge fluctuations, so forget double occupancies or holes or anything like that, just 1 particle per site. And let's say there are absolutely no correlations in the system, no spin correlations in the system. Every site then is independent, and the entropy is just log N per site, right? Where N is the number of colors that I have, so 6 if I'm doing an SU6 experiment. So the absolute minimum entropy I can have without inducing spin correlations is log N. And if I introduce spin correlations, then I can go below that value, right? By correlating different sites, they have less choices in the ways they can sit, and so I can decrease my entropy further. So based on this kind of reasoning, you would expect a plot of correlation something like this, that for SU2, as the entropy is decreased, this blue curve, it's small or, very small until I get down to an entropy of about log 2, and then it goes up. Whereas for SU6, it's very small until I get to an entropy of maybe log 6, and then it goes up. And that's in reasonably good accord with the plot I just showed you. Sorry, went the wrong way here, right? This plot. And actually the numbers don't match up too terrible. So this is the fundamental reason behind why the SU6 case gives you stronger correlations for a given amount of entropy. Now, we'd like to make this simple picture more quantitative, right? And to make this simple picture more quantitative, there are some different ways. So one way is you think about this simple picture as the leading order term in a high temperature series. And back in the day, I sort of did some calculations maybe 10 years ago predicting this effect with Anna Maria Ray when I was first starting my postdoc. And we computed the next order term in a high temperature series. But these experiments are far into a regime where that's not applicable. So we decided to turn to some numerics. And for the SU2 case, this is a famously hard problem of the Hubbard model, but for SUN, it's much harder. So rather than, so for SU2, you have 2 to the 2 times the number of sites is your Hilbert space. But for the SUN, you have 2 to the n times the number of sites is your Hilbert space. And so that makes this extremely, extremely difficult to treat with something like exact diagonalization or any techniques derived from exact diagonalization. Another way we understand a lot about the SU2 case is by quantum Monte Carlo, which is sign problem free at 1 particle per site when you have SU2. Unfortunately for SU6 or any SUN not equal to 2, there's a sign problem even at that unit density, 1 particle per site. So it's really difficult. So what we've done and what I'll show you here is that we did actually implement a QMC code for SUN. There's a sign problem, but we can still push it as far as we can push it and see how well we can do. And the other thing we did is we built an exact diagonalization code, which really takes advantage of everything you'd normally take advantage of, like the translation symmetry, but also the SUN symmetries. Adrian, I think, has a question.
Hey, yeah, how's it going? Is it easy to understand why one gets this sign problem as soon as you go away from SU2? I'm not sure I've ever understood this in a simple way.
Yeah, so let's think about why there isn't a sign problem for SU2. It's basically because you have a particle hole symmetry, and so the determinants you get in the type of determinantal quantum Monte Carlo I'm going to talk about, well, okay, I'm actually not going to talk much about it, but that's what we're doing, determinantal quantum Monte Carlo. You get equal contribution multiplying from the particle determinant and the hole determinant when you're at this balanced case. So if you were at the particle hole symmetric part of SUN, you would be okay. But the issue is for SU6, the particle hole symmetric point is when you have 3 particles per site, not 1. But the physics I'm interested in, because of the experiments and other reasons, is at 1 particle per site. So it's just that you lose the symmetry that matches the pairs of determinants. Does that make sense, or? Maybe. The hand is down. Interrupt me if it doesn't make sense.
Yeah, that does. Yeah, sorry, I was muted and then unmuted again. Thank you.
Okay, just checking. Yeah, okay, perfect.
The fact that it's SU6 and you're at this 1 part, I got it. Okay, thank you.
So if you were at average n equals 3, then you could actually do sign problem free SUN Monte Carlo, and people like Kongjung Wu have done some really nice calculations with that, actually determining the equation of state and things as a function of temperature. So with the ED, which has been very powerful for us, we've used these translation symmetries, used the SUN symmetry, and we also use really a basis truncation, which just says that ignore the tunneling term since we're at such large U. Probably you don't have to include really high energy states like where I have 4 or 5 or 6 particles per site on a bunch of sites. And so we have a systematic truncation that we've converged. You can just ignore it for the things I'm going to show you. It's 1 part in 1,000 or 1 part in 100,000 in many cases. So, so the exact diagonalization we can do up to the finite size effects is pretty exact. And we're able to actually do exact diagonalization this way with about 8 or 9 sites, which may not sound impressive, but it's much, much larger than anyone else had been able to do. The first people collaborating with the experimentalist on this, I think, got stuck around 3 or 4 sites. So so it's not trivial to get there, but there's nothing particularly innovative or clever, just being smart about what you do. So anyways, to remind you, here are the results, SU2, SU6. I'll show you the exact diagonalization extrapolated from finite size scaling from those results. This is what you get. I think this is marvelous agreement. You clearly see this enhanced trend going from n equal 2 to n equal 6. You get the onset entropy of the correlations correct. There are some deviations at low entropy, which are kind of interesting, but it's within a 2-3 times the error bar for the most part. It's I consider this excellent agreement. Let me emphasize there is zero fitting being done here. This is Yoshiro's postdoc, Shintaro Tai, emailed us the trap parameters and told us the U over T. We put that in our code. These curves came out. There is no back and forth with the experiments about like, let's adjust this or let's adjust this. This is really sort of a quote ab initio calculation. No fitting directly from the Hamiltonian. So I think this is very good agreement, all things considered. And so this is for the 1D experiment. Actually, Yoshiro has data for 2D and 3D. Let me show you the 3D results. So this red curve is his 3D results. And here we can do quantum Monte Carlo. That's this red dashed curve. Unfortunately, we can't get very cold with the quantum Monte Carlo in this regime for several technical reasons. So we can't say too much. If you have a mother's eyes, you see that red dashed curve lies below the green one. And so you say that's just like the experiment, but that's about, that's pushing your luck. I wouldn't read too much into that. So this QMC code that I mentioned is very good for computing other things if we're not at such large U, for example, but for this precise experiment that they've done, it's not so useful to compare with the data. But this actually tells you something else that's interesting, which is this 3D data the experiments have at all these low S is way, way, way beyond our ability to calculate theoretically, even using state-of-the-art quantum Monte Carlo or ED tools. So people talk about quantum simulation, simulating new things that you can't calculate using a cold atoms experiment or some other experiment. And I think this is a really a great example of that, in that they're well beyond a regime that the theorists can handle. And so a lot of our work is motivated towards trying to understand what's going on in their experiments in these kinds of regimes in more approximate or analytic ways. Okay. And I'm not sure how fundamentally important this is, but one of the coolest things that sort of just pops out from this is that in fact, they can't measure the temperature in their experiments. They can measure the entropy, but not the temperature. And I'm happy to discuss why if you're curious. But we can ask what temperature is predicted from the theory, given a correlation of the magnitude observed here. And the temperature comes out to be about 0.1 times the tunneling energy. And why that's so exciting is that is in fact the coldest Fermi gas ever created. So as far as I know, the previous record was set by Marcus Greiner's group at about 0.25 times the tunneling energy, and we're 2.5 times colder here. And so, I'm not sure how really important it is to be cold, but it's pretty cool to say that you have the coldest Fermi gas. And it's also cool that as a theorist playing some role in this, since they can't directly measure the temperature. It's really from comparison with the numerics that lets you extract the temperature. Okay, so that's essentially what's been done with the SUN part of the story I want to tell you today. Here's some future work. They actually have already done experiments with bilayers. So they've done 1D, 2D, 3D. They've done a dimerized lattice, and they've done bilayers. There's a prediction of S plus minus superconductivity in the bilayers at actually a pretty high transition temperature. So that's something we're interested in exploring. We're really interested in the phase diagrams. We have these nice numerical tools, including one which I didn't tell you about today, but which at large interactions maybe works better than the QMC for high dimensions. And that's something called a numerical linked cluster expansion. So we are trying to calculate phase diagrams, and especially the kind of finite temperature properties that you get when you're not at zero temperature, but maybe you're cold enough to see manifestations of the ground state. And we're trying to make those connections and ask what does the phase diagram look like, as well as do simple calculations, analytic calculations, things like slave rotor theories to try to understand the doping dependence. What happens when you dope an SU3 system? There's a wealth of really interesting phenomena that are starting to be explored for SU2 of this system, things like the pseudogap, strange metal, bad metals, where people are studying this by looking at transport and spectra in the cold atoms. But there's no reason we can't do all the same things with SUN, and Yoshiro in particular has just built a brand new experiment doing all of this in a quantum gas microscope where he can resolve every single site. And so we're starting to do calculations and trying to understand this. But we're just really, ramping up with this. And then there's been some fun stuff about collective modes. Even without a lattice, you can look at SUN physics and see how in changes things. There are some beautiful experiments done by someone else, Gyubong Zhou at Hong Kong, and you should check that out too, because that's a whole fun direction that we're also exploring. But that's really, so the conclusion of that part of the talk, which was the sort of first half or 2/3 of my talk, is that SUN is this new frontier for quantum matter that's been experimentally realized to high precision in these alkaline earth atoms. We are now quite far along the study of these. We now have larger correlations in colder temperatures than any SU2 experiment. At least nearest neighbor correlations in the coldest temperatures than any SU2 experiment. And there's this whole zoo of exotic states, which we're hoping to figure out. So let me pause there and see if anyone has questions about the SUN stuff before I jump to my closing topic. And I'll drink some coffee. Lucas?
Yeah, hey. Just a quick question at temperature. You said earlier that you can reach way lower temperatures with SUN. Could you essentially use that as a fridge? So to say, you basically cool down the SUN and then blow out say if you have an SU6, you blow out 4 species and then you have a cold SU2 gas.
Yeah, so this is a very, very interesting question about whether you can essentially use the fact that you're cold to generate systems that aren't the SU6 system, but are also cold. And the answer is not obviously, but let's think about what some of the problems are. So if you try doing like what you just suggested, where I blow out some of the species, I have SU6, and now I blow out species 3, 4, 5, 6. What I'm left with is an SU2 gas, but I've put in a ton of entropy by blowing out all of those other spin states, right? So it's a much higher entropy gas. That process increases the entropy so much that the heating overwhelms everything else by far. Now, you might be able to do some more clever things, like where you might think I could adiabatically change something, but if I adiabatically change, I'm not going to change the amount of entropy, and probably that's what really matters, not the temperature. So the best prospect for doing this that I can think of is using the SUN as a coolant, right? So it's just like your cryogen. It's helium-4 that you dunk everything else in, right? And so in principle, you could create a very cold SUN Fermi gas, put another system on it and just let them interact, exchange energy. Then you would expect them to thermalize. And as long as you have enough particles in your SUN Hubbard model so it can absorb the heat, you'll get good cooling. I'm not sure about the practical issues of that, what the sort of heat capacity and the heat transport rates and equilibration rates are to make that work. And I said these are the coldest Fermi gases. And so one question you have to ask is, if I actually want to use sympathetic cooling like that to cool something, is it better to just cool with bosons, which can get very, very cold? Bosons are much easier to cool than the fermions in these sorts of experiments. So I think it's a very interesting question, but it's not obvious that it can be used.
Okay, thank you very much.
Of course. Okay, if there's nothing else, then I will move on to the second part of my talk. And so it's really a totally different topic. So you can leave now if you're bored, or if you're just jumping in, you haven't missed anything, just waking up. So what I'm going to talk about is bounds on how fast information can propagate and how we can use this to understand and do better numerics in many body systems. So fundamentally, the reason, the fundamental statement is that correlations spread at fastest linearly in time. So it's like a light cone, right? And of course, this is obvious because of relativity, but the point is there are stronger bounds. That if I have something like a Fermi-Hubbard model or Ising model or whatever, the actual speed at which the correlations are bounded by is much, much smaller than the speed of light. For this coffee mug, it's probably something like the speed of sound, or for your Ising model, it's probably something having to do with the coupling J between sites. And this is a very plausible sounding statement. And in some sense, it's just common sense that if I have some locally interacting system, I can talk to my neighbor can talk to its neighbor, and each of those steps takes a finite amount of time. So correlations will spread linearly in time at most. You can also convince yourself this by thinking about non-interacting particles, or maybe doing perturbation theory and weakly interacting particles. There's going to be some maximum group velocity if I'm in a lattice, not if I have a non-relativistic system in the absence of a lattice. But if I'm in a lattice with a finite number of bands, there's going to be a maximum group velocity. Or a way that is really helpful for thinking about how to make this mathematically rigorous is to think about short-time perturbation theory. So if you have, say, since we were just talking about a Hubbard model, here's a picture of a Hubbard model. One atom can hop from site to site at a rate of the tunneling. And so in short time perturbation theory, the amplitude for doing that is just going to be like JT cubed, where J is the tunneling and T is the time. Okay, so let's try to make this a little bit more mathematically precise. I'm not going to give the proof to you, but this is what comes out of the proof, and I'll give you a little bit of intuition in how the proof goes in a second. So what the precise statement is that if I look at the commutator between two observables A and B, which are localized in different points in space, that the commutator of these two observables, where one is not time evolved and one is, has to be bounded by something that decays exponentially with x minus vt. Okay, and where x is the distance between these two observables. So that's precisely the statement of the light cone. Inside the light cone, I can't tell you anything about the magnitude of these, or I can tell you very little about the magnitude of these. Outside the light cone, I can tell you that these decay exponentially. Okay. There are a bunch of constants in here, this V, this C, and the C, and those are constants that if you give me a model, I can tell you what they are. And this bound has been rigorously proved for any locally interacting or exponentially decaying interacting system in whatever dimension, whatever graph, whatever Hamiltonian you want, as long as there's a finite on-site Hilbert space. Okay, so that's great, but it turns out that you know, there are some major issues with these bounds, qualitative issues. And the qualitative issues are actually, it's useless quantitatively when you go look at these things. We said we expected maybe in an Ising model, you'll get that the velocity of information propagation should be something like the interaction constant J. Well, it's actually 40 times larger. Sorry, I actually think it's 10 times larger. I think the 40 is a typo on the slide. I think it's 10 times larger. I think the velocity is 40 times J that it predicts. So that's not very good. It's great to know that the bound exists in principle, but if you're actually wanting to test a physical system obeys this or get any information about the physical system, this tells you very, very little. It's not just a quantitative issue. It's loose qualitatively. And I will show you on the next slide an example where the Lieb-Robinson velocity predicted is finite, but the correct answer is 0. So that's bad. The third difficulty is that when you have large spins, which I think I gave you motivation to look at large spins early in the talk, usual Lieb-Robinson bounds actually predict that the velocity of information propagation diverges with the size of the spin. And at least if you normalize things correctly, it should stay finite. Physically, that's what you expect by doing semi-classics or something. But there's never been a proof of this, and Lieb-Robinson bounds have an issue proving this. So let me give you some intuition for how Lieb-Robinson bounds are usually done, and then I'm going to tell you about how we got around all of these issues. So, yep, there's a question. Oh, it's a private question. So somebody asked, why is the information speed in the toric code 0? And the reason is pretty simple. It's that the toric code is a sum of mutually commuting terms, and you'll see why that's important in a second. But the point is I can create a local excitation, and because that excitation, you know, creating that excitation kind of commutes with everything else, that won't hop around. That excitation doesn't hop around. Or put another way, the dispersion of the excitations is flat. And so there won't be any propagation of information there. I'm happy to discuss more privately, but actually I think I'm going to give you the example in the Ising case, and you'll understand why mutually commuting terms are bad for information propagation. So to understand the argument, I'm just going to use this identity. I'm guessing most of us at some point had to prove this in grad quantum course. If not, here's your homework from my talk. But it says that if I time evolve an operator A, I just get the nested commutator sequence 1 plus it h comma a plus it squared over 2 factorial h comma a, right? And this goes on forever. You can prove this just by differentiating both sides. So the way a usual Lieb-Robinson bound works is to ask how far can information propagate term by term. So if I look at the first term, H has some range of interactions. It's a sum of terms which each couple sites within that interaction range. And A is localized to some spatial region. And so whatever this H comma A term is, it's has a support on a set of sites that is within an interaction range of A. Whatever the interaction range of H is, it's within that size of A. So let's take an example. Take A to be sigma x on site 0 of an Ising model. Take a nearest neighbor 1D Ising model. Then this commutator has to lie on sites -1, 0, and 1. Right? So that tells me where the commutator sits. Now when I take this double commutator, I have that thing that sits on these two sites and I commute again, I can extend it by one site, right? So this term is localized to sites within twice the interaction range. And order by order, you can see I go twice the interaction range, 3 times the interaction range, 4 times the interaction range. And essentially what the Lieb-Robinson bound does is just prove that, and then prove that what you get from the higher order terms doesn't mess up what's going on with these lower order terms, right? So essentially I'm bounding this perturbative order by order, and then Lieb-Robinson actually says that it's not just an order by order argument, but I can look at a finite T and get control on the higher order terms as well. But to understand qualitatively what goes wrong, we can see the following. So here we're just using that the support of the commutator is localized within an interaction range of A. But let's consider the 1D Ising model. And I'm going to consider the 1D Ising model with no transverse field. So just a nearest neighbor sigma z term. Now you go compute the commutator and you get something for the first term that site 0 is sigma 0y times some stuff that's sigma z on the adjacent sites. Here I'm thinking about A being the operator sigma, not x again. So it's localized to the sites -1, 0, and 1. It had to be. We gave that argument before. But now when I think about the nested commutator, that sigma z interaction actually commutes with the first commutator as long as it doesn't sit on the sites -1, 0, or 1. So all the terms in the Hamiltonian coming from further away than the nearest neighbor site are all going to end up just vanishing when I take the commutator. And same for all the higher order terms. So actually the operator sigma naught x is localized to 3 sites for all times. It doesn't spread. And so when I take this commutator that I'm interested in, sigma naught x of t with sigma j at some site, this is 0 as long as j is greater than 1. And the usual Lieb-Robinson doesn't have a clue about this. Usual Lieb-Robinson says, well, it's bounded by, this 1 interaction range, 2 interaction range, 3 interaction range. And so what's missing is the commutation structure. The usual Lieb-Robinson bound doesn't know anything about the commutation of the different terms in the Hamiltonian. And in almost any Hamiltonian you ever care about, you're not looking at the kind of worst case scenario. There's a very special commutation structure to any class of Hamiltonians you look at. And so we can capture this by little pictures that we like, we call it the commutativity graph. If I have a 1D transverse field Ising model, I can write the Hamiltonian as a sum of terms, little hj. Some of these are sigma x terms, some are sigma z terms. And what I do is each of these terms gets a node on a graph. And if they don't commute, then I draw a line between 2 terms. And when you draw this picture for the 1D transverse field Ising model, it looks like this. It's just alternating sigma x and sigma z terms, sigma x and sigma z. So it's a 1D graph of alternating types of terms. And you can do the same exercise for 2D transverse field Ising and lots of other cases. You get slightly more complicated graphs, but these encapsulate all of that commutation structure. They tell you that actually a lot of things, even though they're nearby in space, they actually still commute. And then you can basically rederive all the perturbative Lieb-Robinson arguments that I just told you, not non-perturbative Lieb-Robinson arguments that I just told you, accounting for this commutativity structure. We developed a method to do that. And this fixes all of the issues that I introduced. We went from a factor of 10 wrong in the velocity to being within 30% of the correct velocity. It captures the fact that the velocity vanishes in this Ising example I just showed you, as well as the toric code in other cases. And it in fact gets the correct large spin velocity, or at least a finite large spin velocity instead of diverging. Again, because it captures the fact that really you don't have an arbitrary on-site Hamiltonian, you have a very simple on-site Hamiltonian like SX, or nearest neighbor Hamiltonian like SXSX or S dot S. It's not some horrendously complicated thing. Okay, so we're very proud of these bounds as giving fundamental new insights. Let me just close in the last 2 minutes here with telling you an application of them. And it's an application where having these better bounds is absolutely crucial. And so a good motivation for us to do these quantitative bounds and to continue to improve them is this case. And the point I want to make is that finite size errors are ubiquitous. We had them in the results I showed you earlier. You have them in virtually, well, many, many, many methods that people use. It doesn't matter whether you're condensed matter or a different type of physicist. If you're doing lattice gauge theory, you have finite size effects. We saw that cold atoms experiments are finite size. So if you want to learn something about an infinite system, a thermodynamic limit system from one of these finite systems, there are finite size differences and you'd like to know how big they are. And the issue is that right now there are absolutely no guarantees. The best we can do is to do finite size scaling. So I do a size 5 system, a size 6, size 7. I go as large as I can, and hopefully if they agree order by order, I say that's good. But we actually know examples where it can be really, really good for a lot of orders, maybe the highest order you can get to, and then the behavior changes at much larger system sizes. So that's bad to have happen, and you'd like to be able to rule that out. And the other issue is that sometimes we just don't have enough system sizes to do finite size scaling. If I'm doing a 2D system, doing 6 by 6 may not even be possible for many systems. And so I can do 3, 4, 5, but am I going to be able to extrapolate, 3 by 3, 4 by 4, 5 by 5? But it's not at all clear I can extrapolate to the thermodynamic limit from that. So to get around this, it turns out you can bound the error of finite size simulations using Lieb-Robinson bounds. And so I'll tell you just real quick, you can do this for ground states, for thermal states, up to some caveats we can discuss, but it's easiest to think about for dynamics. So imagine a simulation where you start from something that fits in your finite size system, or maybe it's a product state, so the state is somehow exactly captured by a finite size system. And I want to know what is an expectation value at the center of that finite size system. Then the only source of error can come from information propagating in from the boundary. And that's exactly what we learned how to bound by Lieb-Robinson bounds. So we've proved that in fact you can use the Lieb-Robinson bounds to bound the finite size error. And again, it's a few line proof, it's pretty simple. It's useful in practice. Here are some numerical results on a 1D transverse Ising. This isn't special. We can do these bounds for 2D, 3D, non-integrable models. This was just so we could test things. The solid lines here are calculations at different system sizes, 5 sites, 9 sites, 13 sites. And the shaded regions associated with each one are the bounds on error predicted by this method. The method doesn't tell you what the average is, just what the bound on its error is. And you can see that it's pretty good. So look at this 21 site simulation. You see that this error bar is tight out to the time at which this model has kind of settled into equilibrium. And so if I plot sigma x versus time, it kind of settles down, all the oscillations damp, and it shows that your numerics is reliable, 100% guaranteed, no wiggle room. The true thermodynamic limit answer has to lie in those shaded error bars. And so I think that's very valuable. And although it's not, it's a somewhat pessimistic error, if you look at the exact solution, this dashed line, the deviation from the purple curve, the L equal 21 curve, happens at maybe time 4, whereas it happens at maybe time 3.5 from the error bar. But given, that's not a huge difference, and given the rigor with which it applies, I think it's very valid. And we think that we can continue to improve these things. And to give you some hint of, I told you we had better Lieb-Robinson bounds now. To show you how important they are for this application, had we used the previous best Lieb-Robinson bound for this application, you would have got this error bar I'm showing on the left. It's just, I'm cutting it off because it exponentially diverges at some point. And you see you would have had useless error bars already at a time of like 0.4, 0.5, whereas ours works all the way out to here where it's nice and equilibrated. So I think quantitative developments in Lieb-Robinson bounds are important. So that's really the whole story. You can use these bounds if you have a measure of the error on a cluster. You can say, what is the optimal cluster shape to do a calculation? And if you're doing single site observables like sigma x, you get shapes that are probably not what you've been using in your numerical calculations, where you can look at 2-point correlation functions and also get different types of correlations, different types of cluster shapes than what you'd typically use. And they do perform better. We've numerically checked this, which that's just to prove that we've done it. I'm not going to talk you through that. Let me get to the conclusions. This is it. So SUN's a new frontier, lots of exciting stuff going on there. And we have rigorous results for many body systems that let us sort of combine mathematical physics and numerics to get rigorous quantitative errors for our numerical methods. So that's it. Thanks for listening.
Okay, so if anybody has a question, please either raise your hand virtually, or if you're having some trouble doing that, just turn on your video and physically raise your hand. Okay, so Professor Del Maestra.
Thank you very much. That was an excellent talk. I had a question about the error bounds in the last part. So Can one do this for generic types of estimators? I mean, what about more non-local things? Like, let's say I want to know some error on an element of an n-body reduced density matrix.
Oh, so if it was, let me talk about a spin reduced density matrix. So if I had an L-body reduced density matrix of spins, which just means L sites, then absolutely you can get bounds like this. And they tend to be dominated by whatever the site nearest to the boundary is if you're doing open boundary conditions, or if you're doing periodic boundary conditions, it's basically just kind of the error is exponentially small in the length of the system minus the span of the observable that you're looking at. But if you really wanted to look at something that was like spanned the whole system or was an overlap, like a fidelity or something like that, it's not at all clear to me how you would do this. I don't want to say it's impossible. Maybe I should tell Jiwan it's impossible. He'd probably go prove it to spite me, but it's not obvious to me how to do this. That really, you need that notion of locality to use these Lieb-Robinson bounds. We do have other error bounds that he's been working hard on that are not based on Lieb-Robinson. So they're based on other sorts of mathematical physics techniques. And there they work for absolutely any observable things that don't have to be local. I think he can get bounds on.
Mm-hmm.
Okay, any other questions? Oh, okay. So Professor Hooley, you are unmuted.
Great, thanks very much. Yeah, so I agree, that was a great talk. I just wanted to ask a question about the commutation structure.
Mm-hmm.
It was kind of reminiscent to me of the kind of, it looked like setting up transfer matrices for a classical stat-mech problem. Is there any link between the commutation structures you're getting here and what you would do for some bit of classical stat-mech on a related model?
Mm-hmm. So I'm not actually sure I see the connection you're suggesting here. So when I think about doing the transfer matrix for a classical stat mech model, so I definitely get a matrix structure from this. But what's the analog of the commutation structure there?
Yeah, I'm not completely sure. I mean, but you can do these tensor network things for partition functions for classical stat-mech models, and the way the indices come in just feels reminiscent of the diagram you were drawing. It's not a very well-formed question, so if you don't have an immediate thought about it, then
so one thing that I think is that anytime you have a matrix that you're evolving, right? So you have something that's the exponential of a matrix that you're trying to evolve, that really you should be thinking about the commutation structure of it in the time evolution rather than thinking about the real space. That somehow the you really don't lose much by looking at the commutation structure. It's not harder to work with or anything like this, but it gives you a much finer grained handle on what's going on. And so if you are using, you know, maybe this sort of construction emerges when you're looking at integral models and transfer matrices and things. If you have this kind of thing where you're exponentiating operator that's a sum of terms, I do think that looking at the commutation structure of those terms is extremely important. And it's something that I don't know why people don't just take as the default. And so I'm trying to think, because actually the same student, Jiwan, who's worked on a lot of this stuff, has done some remarkable stuff with exactly solvable models that I didn't talk about here today. And so, yeah, I will forward your question to him and see what he thinks. I don't think he's online here, but I will ask him, because if there may be a connection here.
Great, thanks.
Mm-hmm.
Okay, so any other questions? So I actually had a quick question. So in the SUN Hubbard model, if we take the large n limit, could we apply some holographic techniques? And if so, would it tell us something useful?
Oh, that's a really interesting question about holographic techniques. So so being a lattice system, it scares me a little bit in terms of thinking about an exact holographic mapping or a really sort of controlled holographic mapping. But maybe in the case where you don't have a lattice, so you just have an SUN Fermi gas with contact interactions, there might be some closer mappings there. I think that people like Dam Tan Son have even done this for the SU2 case. And so I wonder if doing the SUN case there, you might actually be able to get more control on some of the things they've done. I'm certainly not an expert on this stuff, so I'm not sure. Although you do have to be a little bit careful. So if you don't have a lattice and you take the large n limit, and at least if you're starting from something like a weakly interacting Fermi gas and looking at dynamics from that, or looking at transport, then you can typically get by with Boltzmann equation type stuff. And actually the large n limit will tend to justify dropping the collision terms and the higher order terms. So it can lead to you getting actually strongly interacting gases that are acollisional, just by taking the large n limit. So it's a very interesting question if there's a circumstance where the large n limit here actually gives you something that's sort of like the large n limit you get from these other very different holographic theories. I don't know. Just generally speaking, what you see for SU2, when you dope the system in a lattice, you get these strange metal, all this stuff. You know, holographic techniques have been one of the most popular ways of trying to get a handle on this sort of presumably non-quasi-particle matter, right? And so I would expect that SUN's not going to be different, that this can be a very valuable way of getting some insight into things. But certainly nobody's tried this stuff yet, and we know so little that it's very early days. Yeah, good question.
Okay, thank you. So maybe I'll wait 5 seconds for someone if they want to raise their hand and ask a question. Okay, so let's thank Professor Hazzard again. Okay, so
Thanks,
thank you for
everybody.
coming.